The frequency and period of a spring is determined by Newton's three laws of motion. This can never be avoided, can never be escaped. All motion is governed by Newton's three laws of motion. Again, the first law of motion is all about how mass resists changes in motion. There is no acceleration, there is no change in direction or speed if there is no unbalanced net force. For a spring, there is always an unbalanced net force with the exception of equilibrium. And normally if you're moving, that doesn't last for a very long period of time. Newton's second law is the mathematical application of net force and acceleration. And this is where springs are going to live the most. Newton's third law is all about the interaction between two objects. Again, we won't actually be able to measure directly the force of a spring. However, we can easily see how much force we're exerting to the spring and then apply Newton's third law to the spring to figure out how much force the spring is pulling back. Newton's second law helps us to determine the relationship between mass and stiffness with period. The greater the mass of an object is, the harder it is to change its motion. It takes more time for the object to vibrate back and forth because the mass is always resisting that force trying to create a change. So when my object is at rest and that force tries to get it to move, it is going to resist and it's going to be very hard to speed it up. Likewise, once you get past equilibrium and starting to move away, the force is going to try and slow the object down. But with all that mass in motion, it's going to take a lot of time to stop it just to get it moving again. The stiffness of the spring relates to the strength of the force that the spring can generate for any given distance. The stiffer the spring, the greater amount of force the spring can exert on that object for whatever distance it has been stretched. Greater force means greater acceleration. This means the object will change its motion much faster and it actually takes less time to vibrate. These two properties of mass and stiffness are constantly combating one another and determining the period of a vibration. And this is why when we calculate the period of a spring vibrating, we see an equation that has mass divided by the spring constant. The period of any vibrating spring system where the net force on the system is simply k delta x from equilibrium, we can see the period is equal to 2 pi times the square root of the mass of the object divided by the spring constant. The frequency being the inverse of that, the reciprocal, we just see the reciprocal of that. Instead of 2 pi, it's 1 over 2 pi. And instead of the square root of mass over spring constant, it's the square root of the spring constant over mass. You normally only get one of these two equations. A lot of times you just get the period equation. But if you understand the relationship between period and frequency, it's an easy thing to derive. And what I do is I don't try to get very fancy with any of this stuff. What I just simply do is I say, okay, 2 pi is really 2 pi over 1. And I just simply flip it to 1 over 2 pi. Then I have mass over spring constant. So I just flip that to spring constant over mass, and there is my frequency equation. Please notice though, more mass means more inertia, more resistance. It takes more time to get going. Spring constant means more force, more strength, more acceleration. So it's faster to get going and it takes less time to vibrate. That's really the cornerstone concept here with this equation. People often become very confused with this because they only look at this equation and don't think about the relationship on how mass affects motion or how spring constant affects the force of the spring. And if you just keep that part in mind, this is going to be much easier for you because conceptually, if I increase the mass, I'm definitely going to see a greater period in time. If I increase the spring constant, I'm going to see a decrease in the time it takes to vibrate. If you change some other factor, ironically, my period does not change. The only thing that affects the period is the mass and the spring constant. And this is an easy trap that we have for most people, because then we start changing other factors and people start pondering how that affects the period. And the truth is, it really doesn't. And many people find that very confusing because they go, well, if delta x gets bigger, then the distance that I have to travel gets bigger. So shouldn't it take more time to complete my cycle? And that makes a lot of sense. However, if delta x increases, so does my acceleration. So I'm increasing both distance to travel and the acceleration to aid me in traveling that distance. These actually have a canceling out effect. So delta x actually has no impact whatsoever on my time of motion. This is why one of the first things we used springs for was actually clocks, because I could wind my spring up in the very beginning of the day. It would have this huge vibration. You could hear it go tick, 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 tick throughout the early parts of the morning, and it would keep perfect time. At the end of the day, the spring is almost unwound. It vibrates very slightly. You can barely even hear it, but it's keeping the exact time it was before.